Today, we are going to talk about our final presentation of Team Tired Tracker of SDSU Senior Design 2021. Our team members are Andrew, Fadi, Shan, Al Kawthar, and Arman Shah. The main problem, as we know, physical and mental fatigue can be concentration difficult, especially during mentally demanding tasks. Thus, it's imperative for TSA agents to remain alert at all times. We wish to combat issues with fatigue by assessing particularly repetitive and exhausting tasks to optimize TSA agent work rotation. As a solution for our problem, we created a device that can be written on the wrist to monitor biometrics of the wearer, such as body temperature, heart rate, HRV movement, and positioning. Also, our app is Android app, which is connecting to the device via Bluetooth. Our app can upload device readings to cloud server. The server can gather and process device data using machine learning and then determine the fatigue level of the officer. After determining the fatigue level, the server sends back the fatigue rating to the application. On the right side, you can see our diagram containing our three sensors that can gather data. Then it is connecting to the microcontroller, and the microcontroller is connecting to the application using Bluetooth, and the same thing with the server.
Changes that we made to our initial design. We decided to remove the server because it requires to transmit data over Wi-Fi. Since we're already using Bluetooth communication, Wi-Fi would create an extra point of failure. Additionally, a dedicated server will require TSA to pay for an off-site server or maintain a physical server on site. We solved this issue by moving the machine learning algorithm to the phone. We also decided to scale back the circuitry of the project from a full integrated board to a breakout board. We made this change because the amount of issues which could arise by having a complete board is exponentially greater than that of a breakout board. Testing would also be significantly more tedious and time-consuming with a full-fledged board. Since our PPG is a delicate and specialized component, PCB fabrication took longer than most systems. So any revisions we would need to make to a board would make it impossible for us to complete the project on time. As we continue in the updated block diagram, here are the revisions that we made to our slide as mentioned in slide 5 before. The block diagram reflects our decision to remove the server and replace it with a machine learning algorithm within our phone app.
User experience. The user will be wearing the device. The input will be putting on the device to get the biometric data. The output will be the actual data. The app will be connected to the device automatically. Over time, as data is collected and fed into the app, the data will be scaled 1 through 10. A machine learning model will give a fatigue rating based on data received. Technical details. The physical technology. For the IMU, it will measure the rotation level and use the data to determine the motion. For the PPG, the LEDs on the PPG will emit into the user's skin. The density of the blood the user's vein will vary the intensity of the light reflected. A photoreceptor on the PPG then takes the intensity of the light reflected to determine whether the blood is currently being pumped by the heart or not. MCU. We use Nordic MCU. Once data is collected, we can transmit the data via Bluetooth Low Energy. I2C. The I2C will be communicating to the MCU and to all the sensors. Software technologies. The Bluetooth Low Energy. We use Bluetooth Low Energy to communicate with MCU and the app. App development. App development used Android Studio to make Android Java to handle user interface and machine learning model to process the data. Machine learning takes the input and multiply by its values and then use those values for the output. And for the machine training model, we record the data and use the recorded data to train the supervised model. Performance specifications, sensor accuracy. For the IMU, measures acceleration with 1% accuracy. The PPG measures the heart rate accurately to the nearest 1 BPM. The body temperature is measured to accuracy of 2%. Data rates. IMU transmit data at 52 Hz. PPG transmit data at 50 Hz. Temperature sensor transmit data at 1 Hz. And Bluetooth transmit data at 1 Hz. Physical dimensions. The device is smaller than 2.5 times 1.5 times 1.5 inches.
During this project, we applied what we learned during our SDSU course load, specifically the microcontroller firmware, circuit design, and Android application. For the microcontroller, we programmed the registers to enable and utilize the microcontroller, IMU, body temperature sensor, and PPG. The microcontroller programming applied the skills we learned in our COMPI 375 class and was done through C programming, which we learned in COMPI 160. When the sensors have data to be read, they trigger an internal interrupt, which notifies the MCU. Data is also transferred to the MCU over I2C communication, which operates similarly to the USART communications we use in our courses. We also utilize digital filters on the data from our PPG, ensuring the data was properly converted from raw sensor data values to understandable heart rate values. The circuit of the breakout board requires us to calculate the capacitance and resistance of the I2C communication lines. This is imperative because the improper design would lead to the SDA and SCL lines not charging or discharging fast enough, and either of these instances would result in the MCU and sensors being unable to transmit reliable information to one another, and the entire system would be inoperable. We avoided these issues by applying the circuit analysis and circuit design skills we learned in our EE 210, 310, and 330 classes. For the Android app, we wrote the software in Java, which implements object-oriented programming and event-driven programming, which we learned in COMPI 260 and 365.
So some of the bugs and fixes of our system was first low machine learning accuracy. When we first started out with sample data to train our model, we were ending up with an accuracy of about 25%. And this is pretty poor considering that if we were to just randomly guess the fatigue rating from 1 to 10, that we would have a 10% accuracy. So in order to overcome this, we began normalizing the data values that we fed into the machine learning algorithm. And also by collecting real world data of us wearing the device and self-reporting our fatigue level to use as a ground truth to train the machine learning model, we were able to increase the accuracy up to 75%. Now, if we trained with even more people for even more time, I'm sure the accuracy would be able to increase even further. Another issue was microcontroller timing errors. So a lot of system functionality on a microcontroller used an I2C bus to initialize the system, read from individual sensors, and just general device info gathering. A lot of these I2C functions were based on interrupts, and if they interrupted each other, so one I2C function interrupted another I2C function, it can lead to lost data or even system failure because the data would collide on the I2C bus, and sometimes that would just cause the system to crash because it wouldn't know how to handle the data it received. And something simple like disabling interrupts when the I2C bus is being used, it won't work because even temporarily pausing interrupts on the system would cause the Bluetooth module to crash because the Bluetooth module had some very timing sensitive functions that were running. And if anything paused, it would cause it to miss timing and the system would crash. So the solution we came up with is to establish a low interrupt priority for all I2C functions. And this ensures that any I2C function that interrupted another I2C function would have the same priority. So instead of interrupting, it would be suspended until the current process is finished. And then once it's finished, the interrupt would take place. And this was able to solve our timing errors and stop any I2C collisions that we were running into. And the last major issue we were running into with our system is inaccurate PPG readings during excessive movement. So as described previously, our system detects heart rate by using a PPG, which sends LED pulses at the skin and looks at how the light received varies. But any movement can also cause the amount of light that the system is receiving to change drastically, even for what we might perceive as kind of a small movement. And this can corrupt the data and lead to inaccurate readings. So the solution we came up with is to use the IMU data that we were already collecting and synchronize that with the PPG movement, with the PPG readings, so that for each PPG reading, we would have a corresponding IMU data. So we know exactly how the user is moving during a specific PPG reading. And by testing how values were affected by certain movement, we were able to determine that PPG readings would stay accurate to a movement threshold of about half a G. So by monitoring IMU movement during PPG reading, if that IMU movement passes thresholds that we set, it would mark that PPG data as inaccurate and just discard it. And this allows that all the PPG data that we have to be accurate. So for system validations, we started with a simple system validation that would turn on the device. We would make sure that the sensors are running by looking at the operation LEDs for the PPG, make sure the PPG is running and flashing its green LED. Then we would check on a separate Bluetooth scanner app to make sure that the device is actually advertising it can be connected to, and we can read the data values off of it from its generic attribute profile for the Bluetooth protocol. Once that's done, we begin testing the device with our app, our companion app. So by opening the app, we should be able to see that the device automatically connects to the app when it's turned on. And if we turn off the device, the app will respond and disconnect the device. Once the device is confirmed to be connected to the app, we should be able to see the data readings on the screen, including heart rate, body temperature, battery percentage, and if the user is currently stationary or active. Once that is done, the test will be to do some kind of activity to make sure that the readings are corresponding with that. So the user activity should change from stationary to active. The heart rate and body temperature should rise a small amount. And all of that data should be going into the machine learning model that is embedded in the app. And it should give a fatigue rating for any given situation. So ideally, the system would show that the fatigue rating increases slightly after some activity. With our validation that we have a video that I believe we're gonna play. We were able to show that the device was able to successfully connect to the app. All sensors were working properly with the heart rate, body temperature, and IMU. The I2C and Bluetooth communications were functioning fine. And the phone was capable of understanding what data is being read. And once the data was being fed into the machine learning model, we were able to determine that the model was running correctly. We saw an increase in predicted fatigue as the user was undergoing activity. And from our tests of the training data, we were able to show that the machine learning model was about 75% accurate during any given time.
Over the course of this project, I developed my skills in systems engineering, project management, I2C communication, and machine learning. As a team lead, I was primarily responsible for responding to scheduling issues and ensuring the project stayed on track. For instance, the PCB development process took significantly longer than we anticipated. We had originally only allotted 2 weeks lead time for the manufacturer, but it kept being delayed to nearly 5 weeks. To ensure the project was still making progress during this time, we front-loaded the software and firmware development of the project. So when the PCB finally did arrive, it was a simple matter of coding the board after it arrived. I also worked on developing the first iteration of the completed circuit board, although we ultimately had to scrap it due to lack of time. Nonetheless, that process and my work on developing the I2C communication lines taught me more about circuit development and digital systems communication. Finally, I created the various iterations of the neural network software used in our project. Initially, we used a simple sequential AI algorithm, which simply took the current biometric data to determine the user's fatigue level. This provided insufficient results due to a short-term memory loss, so I transitioned to a time series algorithm, which used past prediction and time-dependent trends as inputs for the current user, which increased model accuracy. Prior to this project, I had no knowledge of how to develop an AI algorithm.
In this project, I learned how to probably break down the project to analyze the specific steps that needs to be taken. Also, I learned how to design an advanced PCB board using KiCad. I learned how to manage working with new software such as Seeger and Embedded Studio, which helped me gain a lot more experience in C language. I gained more experience in testing and how to fix its problems. And finally, I learned how to collaborate with a team effectively in order to get this project done.
So personal development, my role in this project was for PCB design. I was designing the circuit to meet engineering specifications. And it was an interesting challenge because for our PCB design, we needed to balance how the device functioned with user convenience, because a big issue with the TSA was this device needed to be small enough so that the user hopefully didn't even notice that it was there. So trying to balance how we're going to structure these high frequency lines, data lines next to each other in a way that keeps the device as small as possible was an interesting challenge to design for.
As a personal development, for me, I developed my software design skills, especially in C language, and in firmware, I gained more knowledge in embedded system, and also programming sensor to be connecting to a specific microcontroller. And finally, I gained new skills, communication skills, such as working as a group and sharing experiences and ideas to make this project work perfectly.
What I learned during this project. And one thing that I learned during this project was firmware of the sensors. I had to read a data sheet to extract important information for the sensors and then use that important information that is necessary for the sensors and code it and put it in Sager and compile it and make sure it works properly. Another thing I also learned was working together as a team. There are going to be obstacles, whether it's with the firmware, the PCB, or anything else. We just got to find a way to stay motivated, stay on course for the task, and finish it.
The following video is a best use case of our device in action. We begin testing our tire tracker by powering the device on using a button on the side. It connects to the phone via Bluetooth Low Energy, and there's a brief setup period before the device properly reads the wearer's heart rate and body temperature. If the IMU does not detect significant motion, the user is assumed to be stationary. The app displays all data to the user for real-time feedback. After the settling period, the wearer is free to walk around. The system is designed to wait for 5 seconds after motion is detected before the user is declared to be active. This is to avoid misinterpreting short, sharp movements as physical exertion. Lack of consistent pressure on the skin occasionally leads to inaccurate heart rate data, as shown here. To compensate for this, the system takes note of such drastic changes in the heart rate and marks the data as unreliable. The biometric data is then processed by a neural network embedded within the app software. The neural network's predicted fatigue level is then displayed on the bottom left of the screen. This video is a comprehensive test of all of our subsystems, including circuit and firmware design, Bluetooth communication, app development, and neural network design. If our firmware or circuitry for I2C communication had any errors, garbage values would be sent to the phone or completely crash the device. If Bluetooth transmission from the device or the companion app was not properly designed, the device would not connect and no data would appear on screen. If the neural network could not process the sensor data, no fatigue level would be calculated or displayed on screen. Since all subsystems are functioning properly, we have deemed our validation requirements met.